Hi, so this video will cover section 9.1, which is titled Estimating a Population Proportion, right? So this starts a new chapter, chapter 9, which is estimating the value of a parameter, right? So I want to recall a few things, right? So remember, what a parameter is. A parameter is a measurement, from the population, where a statistic is a measurement from a sample, right? So something you want to remember is that oftentimes when we're trying to studying something, we want to know what the parameter is, right? What's going on with the population, but trying to get that measurement is often really difficult, maybe too difficult. It could be really time consuming, really hard, really expensive, right? So for example, if my population was Marion Tech math students and I wanted to send a survey out to all the students to try to get some information, it's likely that I'm not going to get 100% response rate, right? So it's not practical to necessarily get a parameter, right, to get a measurement of the population. So what we do instead is we get a statistic, right? We collect a sample, get a measurement of a statistic, and we can do some things with the statistic to help us estimate what the parameter is, right? And that's what this chapter is going to be about, right? So in the last section, we looked at population proportions, and we're continuing the discussion with population proportions, right? So something else that's important to remember is that the statistic for population proportion is p hat, where the parameter for a population proportion is denoted as p, right? So p is a parameter and p hat's a statistic, right? So in objective 1, we want to be able to obtain a point estimate for the population proportion, right? So I have here a definition. So a point estimate is the value of a statistic that estimates the value of a parameter, right? So in terms of the population proportion, p hat is going to be my point estimate, right? And remember, x is the number of individuals in the sample that has a specific characteristic, and n is my total sample size, right? So I'm finding a percentage of the sample that meets some certain characteristic that I'm studying. Right, so example 1 is to practice this. It says a survey of 2,306 adult Americans age 18 and older conducted by Harris Interactive found that 417 have donated blood in the past 2 years. Obtain a point estimate for the population proportion of adult Americans age 18 and older who have donated blood in the past 2 years, right? So the particular characteristic that I'm looking for is that you have donated blood in the past 2 years, right? So my x value is going to be 417, right? I have 417 people that have that characteristic out of the sample, and my sample size, little n, is this 2,306, right? So what I'm trying to find is the point estimate p hat. So p hat is equal to x divided by n, which this would be equal to 417 divided by 2,306. Right, so if you divide those two, we get 0.181 if we round to 3 decimal places, right? And our book does mention rounding p hat to 3 decimal places, right? So I'll try to stay consistent with that, right? So then now, objective 2, we're going to start constructing and interpreting a confidence interval for the population. So before we get into that, we want to think about some things. So the first idea is that the point estimate for a population proportion will vary, right? So, when we looked at this, in the last section, the idea that if I let's say I'm getting a sample size of 30 people, if I keep random sampling and getting 30 different people, my p hat value, my statistic, is going to be different depending on the group that I have, right? But what we found is that if we meet certain characteristics, the distribution of p hats are going to look normally distributed, right? So maybe something like this, where we have a bell-shaped curve, right, where this is the distribution of p hats, and each of these are individual p hat values that could be possible, right? So it's more likely to have a p hat that's going to be close to the mean, right, which is p, right? So remember, right in the center of this, remember we looked at the mean of the distribution of p hats is equal to p, right? So that's one thing that we need to remember, right? That p hat will vary in the distribution of p hats. The center is going to be p, which is what we're trying to find, right? So a confidence interval, which is what we're going to be after for an unknown parameter, is going to consist of an interval of numbers based on a point estimate, right? So we're going to get a point estimate as sample, and we're going to add, subtract some value to that, and that's going to give us what we know as a confidence interval, right? So then something else that we need to talk about is what's called the level of confidence, right? So we can get different level of confidences when we get confidence intervals. So the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained. The level of confidence is denoted by 1 minus alpha times 100%. Right? So if, for example, let's say I want to get a 95% confidence interval. Right? So if I draw my normal distribution, right, and if I look at this value and this value here, then let's say I pick these values such that I want 95% of my data to be in between them, right? So this value here, if you remember, I can denote it as z and then subscript the area that's going to be to the left, right? So So something that's important to think about is that this alpha value is going to be equal to the area in the tails, right? And the reason why that's the case is because notice that 1 minus alpha is going to be the confidence level. So if 1 minus alpha is going to equal 95, then then if I solve for alpha, right? So I could solve for alpha. I could subtract. Well, this would be times 100% as well. Forgot to write that down. Right, so we would have 1 minus alpha times 100% equals 95. Right, 95%. So then if I divide both sides by 100%, the percent symbols would cancel out, and 95 divided by 100 would be 0.95. So then you'd have 1 minus alpha left on the left-hand side. Right, and then I could add alpha to both sides, subtract 0.95 from both sides. So then what we're left with is 1 minus 0.95, which is 0.05, equals alpha, right? So the alpha value is the area in the tails, right, what I shaded in blue. So we know that a normal distribution is going to be symmetrical, right? So in other words, the area in this tail and the area in this tail is going to be the same, right? Because they're at symmetrical point values, right? So we're going to have 0. Well, in general, we're going to have, alpha divided by 2 in each of these tails, which alpha divided by 2 in this case would be 0.025. Right? So then remember, the notation is if I do the subscript z of 0.025, this value, this number that's a subscript of z, that value, that number, is the area to the right. Right? So then this value over here would just be negative z 0.025. Right? And right in the center would be my mean, p. Right? So then there's maybe some questions we need to think about, like number 1, why does the level of confidence represent the expected proportion of intervals that contain the parameter if a large number of different samples is obtained? And number 2, how is the margin of error determined? Right? So we want to address these questions. So to help answer these questions, let's review some things from section 8.2, right? So the first thing is, if we meet our 3 conditions of a population proportion, right? So one condition is that we need to collect our data randomly, right? Which is satisfied here. And then we also need, right, so I'll highlight, right? So one condition is we need the data selected randomly, which if we do a simple random sample, then we're good. Another thing is that we need this condition satisfied, n times p times 1 minus p needs to be greater than or equal to 10. And then lastly, we need the sample size to be no more than 5% of the population size. Right? And then here, of course, the data obtained randomly is just stated again. And remember, you can make an inequality for this statement. We want little n to be less than or equal to 0.05 times capital N. Right, so you could turn that into that inequality. Right, so if those things are true, then we're going to have a distribution of sample proportions that's approximately normal, right? Where here's my mean and here's my standard deviation, right? So I say here, let's first start by constructing a 95% confidence interval, right? So if I look at this distribution, right? So similarly to before, where I have the mean in the middle, p, and then if I take p minus 1.96, of the standard deviation of p hat, and then p plus 1.96 times the standard deviation of p hat, I would expect 95% of my data to be in between here and here. Right? And before, when we learned like the empirical rule or the 68, 95, 99.7 rule, we said that if your distribution is normally distributed, if you're within one standard deviation of the mean, about 68% of your data will be there. And then if you're within 2 standard deviations of the mean, 95% will be there. And if you're within 3 standard deviations of your mean, you'd expect about 99.7% of the data to be within those ranges, right? Notice we said about. So it turns out that value is actually 1.96 is more accurate, right? So it goes along with my picture up here where I wanted to find, let's say this value here, z sub 0.025, right? Whatever that value is, that's going to be what's called my critical value, which is the number of standard deviations you're away from the mean. Right, so if I actually go to Statcrunch and go to stat calculator, normal distribution, I leave my mean at 0, standard deviation at 1, and then if I go that I want my area to the right of the value to be 2.5%, right, you can see that's where this 1.96 value comes from, right, calculated here. So this value, 1.96, is z sub 0.025, right? it's the critical value where 2.5% of the data is to the right of that value. Right, so that's where that number comes from, that 1.96 value. Right, so then what we're asked now is, 95% of all sample proportions are in the following inequality, right? So all of my sample proportions are going to be within p hat. So if I take a p hat value, 95% of them are going to be in between p plus 1.96 times sigma p hat and p minus 1.96 times sigma p hat. Right? So if I take a sample proportion, I would expect 95% of them to be in between these two values. Right? But what we're trying to do is we want to collect a p hat value, but we're trying to estimate p, right? So ideally what I want in the center is I want p to be in the center, right? So we can do some algebra and solve for p essentially, right? Let's put capital P in the middle. So, to do this you have to be able to solve an inequality equation, right? So let me just write this down. Oops. Right, so one thing to remember, this is a compound inequality. So when you work with this type of equation, you can add, subtract, multiply, and divide, basically like both sides of the equation, but you're going to have to do it to all three parts, right, in the center and both sides, right? So like, for example, if I want to subtract p from, like both sides of the equation, I have to end up doing it 3 times, right? So from the middle and the two sides. But otherwise, it's like solving an equation, right? So let's say I want to subtract p. And something else you have to keep in mind with inequalities is if you multiply or divide by a negative value, you have to flip the inequality symbol, right? Something else to keep in mind. So if I subtract p from everything, of course these would cancel, these would cancel. So what I'm left with is negative 1.96 times sigma p hat less than p hat minus p less than 1.96 times standard deviation of p hat. Right, so I want p hat to be by itself, so what I would do next is subtract p hat from both sides. Right, so then what I'm left with is negative p hat minus 1.96 sigma p hat less than negative p less than negative p hat plus 1.96 times sigma p hat. Right, so I'm almost there. I almost have p by itself, but I have a negative p, right? So I'm going to divide everything by negative 1. And as I mentioned, we're going to have to flip the inequality symbols, right? So instead of them opening, being less than, I need them both to be greater than, right? So what's going to be left in the center, negative p divided by negative 1, is just p. And then over here, when I divide, I have to take each of the terms and divide by negative 1, and that's just going to change its sign, right? So on the left part of the inequality, you're going to have p hat plus 1.96 times sigma p hat. And then over here, you're going to have p hat minus 1.96 times sigma p hat. So if you look at these, right, this value is going to be smaller. So this is going to be the smaller, and this one's going to be bigger, right? So typically when we have an inequality, we like to write the smaller value first, right? So what I can do is flip this inequality around where I write the smaller value first. Right, so we get this. So now p, my population proportion, is going to be in between p hat minus 1.96 times sigma p hat and then p hat plus 1.96 times sigma p hat. right? So then just a note as well, right? So we know that this value p hat, this is known as the point estimate. And then this amount that we're adding and subtracting to both sides, this is referred to as the margin of error. Right? So by adding, subtracting that amount, right, we're allowing for some error to occur, right? Because if I take a sample, it's not going to be exactly equal to p necessarily, right? There might be some error there. So that's why we call that the margin of error. Right? So what this is saying, right, is that 95% of all sample proportions will result in confidence interval estimates that contain the population proportion, whereas 5%, right, which is alpha, of all sample proportions, those are those in the tails above, will result in confidence interval estimates that do not contain the population proportion. Right? So if we get a p hat in these tails, right, it's not going to be not going to be contain the population proportion. Right? So what this is saying is write the 95% confidence interval in the form point estimate plus minus margin of error, right? So the point estimate is p hat, and the margin of error was 1.96 times sigma p hat, right? So that's what they want us to write there, right? So if I add, subtract the margin of error, then I get the lower and upper bound of my confidence interval. Right? So the margin of error for a 95% confidence interval for the population proportion is going to be 1.96 times sigma p hat. This is going to determine the width of the interval, right? Where the width is the difference between the lower and upper bound, right? How wide it is, right? So now what I would like to look at is going through an activity to help make this a little more concrete, right, using Statcrunch, right? It can make a good visual. So if you have your notes out, you can follow along, right? There's directions. So the first thing is to go to the Statcrunch menu and then click on Applets. And then we're going to go to confidence intervals and then for a proportion. Right? And it says to check the proportion with characteristic. So that's already checked, radio button. We want to set the p-value to be 0.3. And then we want to hit compute. And I'm going to reset this. So we want the sample size to be 150, is what we were told to do. And then we want to so note that, you know, having the sample size be 150, that's going to assure that the sampling distribution is approximately normal, right? So we have a really big n value. It's going to make that ensure that it's normal. So then if I click 100 intervals twice, so I get 200 independent simple random samples of size n equals 150, right? So I hit it twice, so once and twice, right? Then down here, this tells me what my confidence interval level is, and this tells me the number of confidence intervals below that contain p, right? So this dark line here, right, this is drawn at 0.3, so that's where my mean is located, right? My p-value, my population proportion. And then what the computer has done, right, what Statcrunch has done is they've selected point estimates, p hats, and then made confidence intervals about them, right? So the confidence interval, you're going to be adding, subtracting values in it and getting like a range, right? So like if I hover over this red one, it says that my sample p hat was equal to 0.2, and my lower and upper limit was 0.136 and 0.264. So notice that my upper limit is 0.264, so it's not going to reach or cover the true population proportion, which is 0.3, right? So in other words, if you pick this apart, if you look at these like diamond-shaped values, or dots, or to me they look more like diamonds, those are your p hat values that were calculated, and then the bar is going to the left and to the right, but the margin of error, and so it's showing the width of the confidence interval, right? So what we have here is we have 200 different confidence intervals. The ones that are green, cover the population proportion. They include the population proportion, where the red ones do not contain the population proportion, right? Either the interval is completely to the left, so in other words, your p hat was too far to the left to cover it, or your p hat value was too big, like with this one here. My p hat was 0.387, and my lower limit's 0.309, so it's not going to go close enough to that, right? So when we say 95% confidence interval, what we're saying is if we get a large number of confidence intervals, that 95% of those confidence intervals are going to cover your population proportion value, right? So we had 188 that contained P, the true population proportion, out of 200, which gives me 94% of the confidence intervals that contain the population proportion, right? So that's where we get the 95% confident. So of course, if I kept doing this, like if I do 1,000 intervals, and I keep hitting it, notice I'm going to get closer and closer to having 95% of them including the population proportion, right? So you can see how that number is getting bigger and bigger, right? So far I've done 19,200 different intervals, confidence intervals, and we're at roughly 95% of them contain the population proportion. All right, so it's something you can play around with if you'd like. All right, so let me go to reset this and hit 100 again, and we get roughly 0.935, roughly 94% of the population of the confidence intervals contain the population proportion, right? So because we need to be able to write that down, and if you do this, you might get a slightly different value, but it's going to be roughly the same, right? You should have somewhere around like 93, 94, 95%. Right? So it says, what proportion of the 200 intervals include the population proportion? Right? So I have, or the one we just did, 93. Whoops, let me get different color. 93.5% of the 200 intervals contain the population proportion, right, which is P equals 0.3. Right? So then part B, it says, what causes the interval to not include the population proportion, right? So this happens when P hat, your sample proportion, is too far away from P. Right? In other words, your P hat is like in the tails, right? So what that means, we could write that down, right? So in other words, your P hat sample is located in the tails, right? So we could also say, in other words, P is less than P hat minus 1.96 times the standard deviation of p hat, or your p value is going to be greater than p hat plus 1.96 times sigma p hat, right? In other words, it doesn't fit in that interval that we just had, right? It's not contained inside of here, your p value. Right? So then to show that a little more visually, right, it says, whether a confidence interval contains the population parameter depends solely on the value of the sample statistic. Any sample statistic that is in the tails of the sampling distribution will result in the confidence interval that does not include the population parameter, right? So like here's a drawing, right, of what we had. So this is still 95%. So right in the center is going to be my p-value, my mean of the p-hat distribution, right? And then you can see, like, if I pick p-hat sub 1, which is this value that's in pink, then this part is showing the confidence interval, right? So it's going to be wide enough, to include your p-value, right? Where if you look at the value of the blue, that's p-hat sub 2, right? Notice this is in the tail, right? It's past the cutoff, right, to be within the 95%. So then if you look at the confidence interval for that, right, which is this p-hat, right, so we're adding, subtracting a margin of error, the biggest value doesn't cover p, right? This part here, it's too short, right? So that's when that happens, right? So that's a visual for what I meant by if your p-hat is in the tail, then that's going to cause the confidence interval to not include the population proportion p, right? So then this statement in a box is some words of caution, and this is, the reason why we went through, what do we mean by confident level is because they're often not interpreted correctly, right? So I think what some people want to say is that a 95% confidence interval means that there's a 95% probability that the interval contains that parameter, but that's not true, right? It does not mean that, right? So note this first sentence. And the reason why, so remember that probability is going to describe the likelihood of undetermined events, right? So therefore, it does not make sense to talk about the probability that the interval contains the parameter, since the parameter is a fixed value, right? The parameter doesn't vary, it's some fixed value. So that's why it doesn't make sense to talk about probability, right? We need some undetermined event, right? So this event's already determined. So think of it this way. If I flip a coin and obtain a head, and then if I ask you to determine the probability that the flip resulted in a head, it would not be 0.5, right? Because the event is not undetermined, it's already determined, right? I already know what the event is. So instead, that probability would be 0 or 1, right? Either it happened or it didn't happen. So confidence intervals work, the same way. So because p or mu, right, these are both parameters, the population proportion and the mean, these are already determined values. So that's why we don't say that there's a 95% probability that the interval contains p or mu, right? So before, what we looked at was calculating a 95% confidence interval to give us something a little more concrete. So now we want to look at this in a more general way. What's a method for constructing any 1 minus alpha times 100% confidence interval, right? So we have a diagram drawn here, right? So in the center we still have p, and then over here we have p minus z alpha divided by 2 times sigma p hat, and then p plus z sub alpha divided by 2 times sigma p hat, right? So before, this number here, remember, was 1.96, but that's because that was equal to z sub 0.025, right? And that's the critical value that has 2.5% of the area to the right of that value, right? But in general, remember that I'll circle or shade these in red, right? So remember, these tails, the sum of that area, right? So the area of the tails equals alpha, right? So that means this area is alpha divided by 2, and this area over here is alpha divided by 2, right? So that's why, we have this z sub alpha divided by 2 here using that notation, and then since it's symmetrical, this over here would just be the negative of that, right? So that's why we subtract it off from there, right? And that's how we can get that margin of error, right? So this is just in general, right? So in other words, p hat would be plus or minus z sub alpha divided by 2 times sigma p hat, right? Where this is my point estimate, and this value here, right, is my margin of error, right? But I know what sigma p hat equals, right? So we know from the last section, right, that sigma of p hat is equal to the square root of p times 1 minus p divided by n, right? But something to remember in this context when we're doing these confidence intervals is we don't know what p is, right? P is unknown. So what we do is we set p to be approximately equal to p hat, right? Because that's the best measurement we have for p is p hat, which is what we obtained from a sample. So what we do is we basically say that sigma p hat is approximately equal to the square root of p hat times 1 minus p hat divided by n, and we're going to use this value to get the sigma p hat value, right? So if I plug that in over here to this equation, right, then what I would have is that p hat, I take p hat plus or minus z sub alpha divided by 2 times the square root of p hat times 1 minus p hat all divided by n, right? So this gives me my confidence interval. And this value here, this z sub alpha divided by 2, this is referred to as the critical value. Right? So then if you wanted to show this in an interval, right, you could take this value here, right, this one, and write it as p is going to be in between p hat minus z sub alpha divided by 2 times sigma of p hat times 1 minus p hat divided by n, and p hat plus z sub alpha divided by 2 times square root of p hat times 1 minus p hat divided by n, right? So you could get this, this is a general confidence interval that we did earlier, or you could write it where you do p hat plus z alpha divided by 2 times sigma p hat, right? So instead of writing filling in the equation for p hat, you could just write sigma p hat, right? So it just depends on what you're after, right? So these are all ways of looking at the confidence interval generalized. Right, and as I said, this value z sub alpha divided by 2, that's called the critical value, right? So we have this table. This is a table of common level of confidences. So 90, 95%, 99%. These are commonly used. We can, if we know the level of confidence, we can find their critical values. Right, and then this box here will help us interpret a confidence interval. So a 1 minus alpha times 100% confidence interval indicates that 1 minus alpha times 100% of all simple random samples of size n from the population whose parameter is unknown will result in an interval that contains the parameter, right? So as we looked at in that activity. Right? So as I was saying, these are common levels of confidence. Commonly used, right? So in example 2, what I have is determine the z sub alpha divided by 2 that corresponds to 98% level of confidence, right? And I picked one that's not common, so that way you could figure out these values on your own as well, right? So the general idea, right, if I draw a normal distribution, is that I'm going to have 2 marks here and here, right, that are going to be, symmetrical marks about the mean. And what I want in between here and here is 98% of the data, right? So that leaves 2% left, right? And the tails are going to match the same area. So I know that in this tail, there's going to be 1%. And also in this tail, there's going to be 1% of the data, right? So this is z sub alpha divided by 2, and this is a negative z alpha divided by 2, right? Those are what those critical values are. I'm trying to figure out what is z alpha divided by 2. What is the critical value? Well, this is going to equal z sub 0.01, right? And remember, that's because of the notation. This is the area to the right. And I'm trying to find the cutoff value that has 1% of the area to the right. So to be able to find this, I need to go back to Statcrunch and go back to my normal calculator. So my mean 0, standard deviation is 1. I would have x greater than, and I want, so instead of 2.5% of the area, I want just 1%. And we get this value here, which is 2.326 if we round to 3 decimal spots. Right? So this is equal to 2.326. Right? So what we found is the lines in the sand, where if I take that value and negative of that value, it's going to get me 98% of my data that's symmetrical about the middle, the mean. Right? So then that would be the critical value that I use, right? So if you want to practice this more, you could verify these critical values that they're correct, right? So I recommend that. So we kind of already did the 1.96, so you could verify the 90%, 99% for extra practice, right? And you have the answer there, so you could check, right? So then just to kind of summarize some things we've been talking about. So when we want to construct a 1 minus alpha times 100% confidence interval for a population proportion, right, you're going to suppose that a simple random sample of size n is taken from a population, or the data are the result of a randomized experiment, and then the confidence interval for p is given by the following quantities. You're going to have a lower bound and an upper bound, right? And we find these by taking the point estimate, adding and subtracting the margin of error. Right? And note here, just as a reminder, that we need those conditions to still hold true, right? So if we're doing a simple random sample up here, and so that's one condition, and then conditions 2 and 3 are mentioned in the note, right? So we're understanding that those 3 conditions are still holding, right? Because if not, we don't have a normal distribution, and this thing all falls apart, right? Isn't going to work right. So we need those conditions to ensure that we have approximately a normal distribution. So as I mentioned, the margin of error, something new is we often use capital E to denote margin of error. So this is an equation to find the margin of error. Right? So in other words, if we take p hat plus or minus E, that's what's going to give us the confidence interval. Right? So it's just a little more concise way to write that. All right, so now what I'd like to do is practice constructing a confidence interval. Example 3. So it says construct a 90% confidence interval of the population proportion given the following information. We know that x equals 30 and n equals 150. Right? So since we're doing a 90% confidence interval, that means that alpha is going to equal 10%, right? Because that would be the area left over in the tails. So that's equal to 0.1, right? So we're going to need that, right? So in other words, what we need to know is what's z sub 0.1 divided by 2, which is z sub 0.05, which is equal to, so actually this one's in the table above. So for 90% we use 1.645, right? So this is 1.645. So this is my critical value that I'll be using to construct my confidence interval. So then what I need to know is what my point estimate is, p hat. So that's found by taking x divided by n, and I know what my x and n values are. X is 30, n is 150. So if I take 30 divided by 150, I get 0.2. Right? So then for my lower bound, I need to take p hat minus z sub alpha divided by 2 times the square root of p hat times 1 minus p hat divided by n. So I have all these values, I just need to plug them in. So my point estimate p hat is 0.2, and then we'd have minus, my critical value is here, 1.645. That's my z sub alpha divided by 2. And this would be times the square root of 0.2 times 1 minus 0.2 divided by n, which is 150. Right, so if we simplify that in your calculator, you get 0.1463 if we round to 4 decimal places. Right, so then now I need to find my upper bound, which is just the same thing but adding the margin of error. Right, so we would have the same thing, just a plus. So if you do second entry on your calculator and just change the minus to a plus, that's how I do it, the easiest way to do it. That would give you 0.2537. Right, so some people report these by saying lower bound, right, and then a colon, and then writing that value 0.1463. And then upper bound, colon, and then what that value is, 0.2537. Right, so that's one way that people report these. Or some people will show them as an interval. Right, so we would write the first number, comma, and then 0.2537. And these parentheses, mean we don't include those values. Right, so they show that in that fashion. Right, so you can find a confidence interval using Statcrunch as well, right? So let me show you how to do that. So you're going to go to Stat and then look for proportion stats, which is here, and then you're going to go to one sample, and then we want to do with a summary, right? So we don't have the actual data, we have a summary. If you have the actual data, so if you're given like an Excel file and given all the information, you would go with the data, right? But we're going to go with summary, and then the number of successes is your X, right? So we put 30 in here. The number of observations is 150, right? That's your sample size. And then we're doing a confidence interval, so you need to hit this button here. And then the level I'm after is 90%, right, which is 0.9. And then you're just going to leave that be the same, and then hit compute. And I get this table, right? So some things on here. is that it does give me my count, my x value. It gives me n, which is 150. It gives me what my sample proportion would be, which is 30 divided by 150, so that's my p hat. And then it gives me the standard error, right? And then the lower and upper limit, right? So all of those are matching up. All right, so ready to look at example 4. So this one says, based on a Pew Research poll, the proportion of parents who say children should be financially independent from their parents by age 22 or younger is 0.64. The survey was conducted on 9,834 parents, and the margin of error was reported at 0.015 with a 95% level of confidence. Determine and interpret the confidence interval for the proportion of parents who believe children should be financially independent from their parents by the age of 22 or younger. Right? So just to write down some things, this 0.64 is my p hat. So p hat is equal to 0.64. So this number here is my n. N equals 9,834. Right? Collected results on that many parents. And this value here, 0.015, that's my margin of error, so that would be capital E, right, the margin of error. And so what I'm after is trying to find the confidence interval, the lower and upper bound, right? So in this case, I actually don't have to do as much calculation, right? I'm essentially thinking of this as the p hat plus or minus e, right? That's simple because I already know what the margin of error is, so that takes away a lot of the calculation, and I already know what p hat is. So the lower bound would be equal to p hat minus e, the margin of error, which in this case would be equal to 0.64 minus 0.015, which that equals 0.625, right? And the upper bound is found by taking p hat plus e, which is equal to 0.64 plus 0.015. So that equals 0.655. Right, so we could report it like this, or if you want to do an interval, it would be 0.625 to 0.655, right? So we're 95% confident that P is in between those two numbers, right? So we could interpret that. So we could say we are 95% confident that the proportion of parents who say children should be financially independent from their parents by age 22 or younger is between 0.625 and 0.655. Right. All right. So now in example 5, we're told that if a sample proportion is equal to 0.55, right? So in other words, p hat equals 0.55. I want to determine which of the following which of the following could represent 90% confidence intervals for the population proportion. So I have 5 options, and I want to see which ones fit, right? So what I'm looking for is I want p hat to be right in the center, right? Because you find the confidence interval by taking p hat plus or minus e, right, the margin of error. So you're adding, subtracting the same value, right? So p hat, if you look at this on a number line, right here is going to be p hat, over here is going to be p hat plus e, and over here is going to be p hat minus e. So this value in between each of these are e units, right? So p hat should be right in the center of your lower and upper bound of the confidence interval. So if I look at part A, if under a little bit of inspection, right, you can note that if I take p hat plus or minus 0.05, then this one works out, right? Because what we would have is 0.55 minus 0.05, which equals 0.5, the lower bound. And if I take 0.55 plus 0.05, then I get 0.6, right? So this one checks out, right? This one's good, right? So I'll circle the ones that apply, right? So if you look at part B, we have 0.53 and 0.59. So if I look at 0.53, I'm going to have to add 0.02 to it to get it to be equal to 0.55, right, which is the population proportion. Where in the second one, right, if I take right, so let me rewrite this, right? So basically what I was noticing for the lower bound, right, the lower bound is equal to p hat minus e, right? If I take 0.55, which is p hat minus 0.02, then that's going to get me at the lower bound, which is 0.53, right? So it looks like maybe e is equal to 0.02, right? But if I take p hat plus this e value, right, this would be 0.55 plus 0.02, which is equal to 0.57, right? But the problem here is the upper bound is 0.59, right? So in other words, p hat is not in the center of B, right? So that one doesn't work, right? So I'll cross that one out. That one's bad. Right? So now let's look at C. So for C, if I take p hat minus e to get my lower bound, right, this would be 0.55 minus, and then in order to get the lower bound of 0.52, I'd have to subtract 0.03, right, to get this lower bound. So then if I take p hat plus e, which would be 0.55 plus 0.03, that would equal 0.58, right? Which that one works, right? The lower and upper bound is going to match. So we have a consistent margin of error. So C is good. Right, so far we just have those two. D, immediately looking at that, I know that one can't possibly be a confidence interval because it doesn't contain p hat, which is 0.55, right? D goes from 60 to 70, right? 0.6 to 0.7, and that 0.55 is not in the middle between that at all, right? So part D, I know that 0.55 is not within the interval 0.6 to 0.7, right? So therefore that one can't possibly be it, right? So you can just scratch that one off. And then for part E, being consistent here, if I take p hat minus e, that should equal my lower bound, which would have to be 0.55 minus 0.1, right, in order to make it be 0.45. So it appears that E is equal to 0.1, right? So then if I take p hat plus E, this should equal the upper bound, right? So this would be 0.55 plus 0.1, which is equal to 0.65. But here the upper bound says it's 0.6, which that can't be true, right? So in other words, p hat doesn't lie in the center between those two values. So that one doesn't work either, right? So the only two that could be possible are A and C, right? So now we're ready to look at example 6. So it says determine the point estimate of the population proportion, the margin of error, and the number of individuals in the sample with a specific characteristic x, given that the lower bound is 0.201 and the upper bound is 0.249. Right? So let me label here what we have. Right? So we have 0.201, comma 0.249. That's my confidence interval. And what I want to know is, and I also know that n equals 1,200. Right, so those are the two values that I'm given. So what I'm trying to figure out is what's p hat equal to, the point estimate, what's the margin of error, E, and also what's the number of individuals in the sample with a specified characteristic, or x. Right, so I want to know what are these three numbers. Right, and so we're given enough information, we can figure this out. Right, so something that's important to note is that p hat is going to be in the center, directly in the center between these two things. So in other words, p hat is going to be the midpoint between those two values. So if you remember back from algebra, how you find a midpoint is you average the two numbers, right? So in other words, p hat is going to be equal to the upper bound plus the upper bound divided by 2, which this comes out to be 0.225. Right, so this is the number right in the middle between these two numbers, 0.225, right? And then something else we know is that the upper bound is equal to p hat plus E, right? Plus the margin of error. So I know what the upper bound is. I now know what p hat is, so I can solve for E. So the upper bound is 0.249. P hat is 0.225. And we're trying to solve for E. So then if I subtract 0.225 from both sides, I'm left with E on the right-hand side. On the left-hand side, we would have 0.024, right? So E is equal to 0.024. That's the margin of error, right? So then next, lastly, what I need to find is x, right? So I have an equation, p hat equals x divided by n. So I know what n is. I know what p hat is. So I can plug in what I know and solve for x, right? So p hat is 0.225. N is 1,200. And we don't know x, right? So then I can multiply both sides by 1,200. And I get x equals 270. Right, so I was able to find all of those values. Right, so there's just some more practice with margin of error. All right, so now what I want to look at is the idea that the higher level of confidence that you get, the wider your interval becomes, right? So like if you look here where this is labeled figure 1, you're going to get your guess, your point estimate here, right? And then you're going to add a margin of error to get your level of confidence, right? but it's going to be smaller, right? The width is going to be smaller if you have a lower level of confidence. That's what this is trying to show, right? So if you have a higher level of confidence, your interval gets wider, right? So like if you look at this next figure below, this gives you an example. So if my p hat was equal to 50%, you can see this represents a 68% confidence interval. This width is 95%, and then the next one's 99.7%, and the last one's 99.99%, right? So as the confidence level increases, the width increases, right? And if you think about the equation, right, for the confidence interval, where you take p hat plus or minus z sub alpha divided by 2 times the standard deviation of p hat, right? What's happening are, in these cases, this value is going to stay the same and this value stays the same. What changes with your confidence level is this value. So this is going to change. And your z sub alpha divided by 2 is going to increase as your confidence level gets bigger because you're moving further away from the mean, right? So since that number is getting bigger, that's a multiplier, it's going to make your margin of error increase. So of course, when you add and subtract a larger number, it's going to make that interval wider, right? So that's kind of the rationale from that, right? So that's a important concept to note. So like here in example 7, it says to put the following in order from narrowest to widest intervals. Assume the sample size and sample proportion is the same for all 4 confidence intervals, right? So we have 4 confidence intervals, and the only thing that's varying is the confidence level. So all you do is you just put the percents in order, essentially, right? So B would have a smaller, a narrower interval than D, than A, and that would be less than C, right? Or in other words, the 80% confidence interval is going to be narrower than 90%, and that's going to be narrower than the 95% confidence interval, and that's going to be narrower than the 99% confidence interval. Right? So if p hat is here, right, then 80% might be like this. Then 90% is going to be a little wider, and then 95% is going to be even wider than that. Right, maybe let me draw this off to the side. Need a little more space. Right. So the general idea is if p hat is here, that's going to be the center. So 80% might span this much. And then 90% is going to be even wider, right? But it's still going to be centered about p hat. And then 95% is going to be even wider than that. And then 99% is going to be even wider than that. Right? But they're all centered about the same value, right? Because they all have the same p hat. Right? So as confidence level goes up, the interval gets wider. All right, so now I have example 8. So we have in a USA Today / Gallup poll, 768 of 1,024 randomly selected adult Americans age 18 or older stated that a candidate's position on the issues of family values are extremely or very important to determine their vote for president. Right? So this problem, we have multiple parts to walk through. So first, let me just label some of the information given to us, right? This 768 is going to be my X value, right? Those are the number of people that fit that characteristic we want, where their family values are extremely or very important. The 1,024, that's my sample size, that's N. So then in part A, we want to obtain a point estimate for the population proportion of the adult Americans age 18 or older for which the issue of family values is extremely or very important to determine their vote for president, right? So I want to calculate p hat, which is equal to x divided by n. So my x value is 768 divided by 1024, my n value. So this comes out to be equal to 0.75. Right, so I have that point estimate value. Part B is I want to verify the three conditions, the three requirements for conducting a confidence interval, right? So that way we have a normal distribution, right? So remember, one of them is that we need the data to be randomly collected, right? And we're told that these individuals are randomly selected, right? So this is met because we have these were randomly collected. The second condition we need, which is important for independence, is that we need little n to be less than or equal to 0.05 times capital N. Right, so I don't know the population size, but what I do know is little n. So if I plug that in, I can solve this for big N and see if it's reasonable to assume that the population is at least that big, right? So little n is 1024. Right? So then if I divide both sides by 0.05, what you end up getting is capital N has to be greater than or equal to 20,480, right? So it's safe to assume that there's at least 20,480 adult Americans, right? Even if you narrowed it down to, adult Americans in, I don't know, Franklin County, right? then you're good there, right? That's pretty specific, but we definitely have at least 20,480 adult Americans, right? We have millions of adult Americans. So we can say that there are at least 20,480 adult Americans. So this condition is satisfied. So then lastly, the third condition that we need is we need n times p times 1 minus p to be greater than or equal to 10, right? But same idea as before, we don't know what p is, but we know what p hat is. So we're going to say that p equals p hat. Right, so if I plug p hat in for p, on the left-hand side of this, I would have 10,024 times 0.75 times 1 minus 0.75, which equals 192, and that's clearly bigger than or equal to 10, right? So that condition is also satisfied, right? So we verified all of those conditions then. So then now for part C, we want to construct a 95% confidence interval, right? So what I need to know is the critical value z of alpha divided by 2 for a 95% confidence interval. So you could look back at that chart from before, or if you remember, we used this one already, it was 1.96, right? A 95% confidence interval is probably the most common, so that's going to be a number that you're gonna remember if you do enough problems, right? So then we need to find the lower and upper bound of this confidence interval. So a lower bound would be equal to p hat minus your critical value, z of alpha divided by 2, times p hat times 1 minus p hat, all divided by n. So if we plug in the values, all these values that we know, this would be 0.75 minus 1.96 times the square root of 0.75 times 0.25 divided by n, which is 1024, right? So plugging that in your calculator, you should get that that's approximately equal to 0.723, right? Rounding to 3 decimal places. So then the upper bound, right, remember the only difference is we're going to add. So we would take p hat plus the margin of error. So that gives you 0.777, right? So my confidence interval is 0.723 to 0.777. Okay. So then part D, we want to find the confidence interval at 99% now. Same thing, but we're increasing the level of confidence. Remember, what should be happening is my interval should be getting wider, right? So my critical value for 99% is 2.575, right, from the table. So notice, 2.75 is greater than 1.96, right? So again, that's what's going to cause that to widen, right? So the lower bound, right, that's going to be equal to p hat minus the critical value times the standard error, which is, sigma of p hat, right? So that would be p hat times 1 minus p hat divided by n, which is equal to 0.75. So the only thing that changes is this critical value. So instead of writing 1.96, we're just going to write 2.575. But everything else will look identical. Right, so this lower bound comes out to be approximately equal to 0.715. And the upper bound will be p hat plus the critical score times the standard error, which is 0.75 plus 2.575 times the square root of 0.75 times 0.25 divided by 1024. And keeping with rounding 3 decimal spots, this comes out to be 0.785. Right, so this confidence interval is 0.715, 0.785. Right, so notice when we're comparing these two, right, that I'm highlighting in green, notice the lower bound becomes a smaller number, and the upper bound became a bigger number. In other words, the interval is widening, right? It's getting wider. So in part E, it says, how do part C and D compare, right? Why is this the case? So the 99% confidence interval is wider than the 95% confidence interval, right? And this is because, we're going to have a higher value of the critical value makes the margin of error wider, right? So then in part F, it says, is it possible that the proportion of adult Americans age 18 or older for which the issue of family values is extremely or very important in determining their vote for president is below 70%, right? So, if we look at the 95% or the 99%, notice that 70% is less than the lower bound in both cases, right? So in other words, it's not within the interval, right? Then what it's asking is, is that possible? And yes, it's possible, right? It's possible to happen. So it is possible, but not likely, right? And that's what that question is asked about, right? So we're, if we're 95, 99% confident that my population proportion is going to be in between these two values, it's possible that it's actually outside of this range, right? We looked at that, but that's only going to happen 1% of the time, right? That's what part D is saying, right? So if I collect, 1,000 population proportions p hat, then only 10 of them, if I did 1,000 samples, only 10 of them would be out, we would expect to be outside, not include the p hat value, right? So it's possible that this p hat value gave us something that's outside, of that interval. In other words, that p hat's in one of the tails, but it's not likely for that to be the case. All right. So now, in objective 3, what we would like to do is determine the sample size necessary for estimating a population proportion within a specific margin of error, right? So in other words, what I want to do is solve the margin of error equation. I want to solve that for n, right? So since we're already at, well, I can do this really quick, right? So so what we have is E equals Z sub alpha divided by 2 times the square root of p hat times 1 minus p hat divided by n. I want to solve for n, right? So first, let's divide both sides by Z alpha divided by 2. Right, so then what I get is E divided by Z alpha divided by 2. That's equal to the square root of p hat times 1 minus p hat, all divided by n. So now what I can do is to get rid of that square root is I'm going to square both sides. Right, so squaring both sides gets rid of that square root. So then I'm going to get just what's underneath the square root left, which is p hat times 1 minus p hat divided by n. And then on the left-hand side, when you take a fraction, square it, you have to apply the exponent to the numerator and denominator, right? So this would be e squared divided by z alpha divided by 2 squared, right? So that's an exponent rule. So then now to get n by itself, I could multiply both sides by n, right? So multiply by n, multiply by n. So then what I'm left with is n times e squared divided by z sub alpha divided by 2 squared. That's equal to p hat times 1 minus p hat. So I'm trying to get n by itself. So now what I need to do is divide both sides by e squared divided by z alpha divided by 2 squared. Right, so that will get rid of that on the left and leave just what we want. Right, so that's going to leave me with n equals, so when I divide fractions, that's like multiplying by the reciprocal, right? So I would have p hat times 1 minus p, and this would be times the reciprocal, which would be z alpha divided by 2 squared all over e squared. Right? So then now what we can do to make this a little less confusing is I can take the exponent of 2 out and put it back like outside the parentheses, right? So this would be n equals p hat times 1 minus p hat times z alpha divided by 2 over e. That whole thing's quantity squared, right? So it's kind of like doing that exponent rule in reverse, right? And so that's helpful because, when you have z with a subscript and that has a 2 in it and then it's like squared, it just this is just written a little easier, right? So what this allows us to do is get an equation to where we can try to figure out what n value should we have in order to get a specific margin of error, right? And so when you read below here in this box, it says if you know if you know the margin of error and you know the population proportion, the point estimate p hat, then you're going to round up to the next integer, right? And then it says here in the next statement that if you don't know what p hat's equal to, right, you're going to let p hat equal 0.5, right? So you're going to plug in 0.5, which that gives the equation 0.25, right? If you plug that in, because you would take 0.5 times 1 minus 0.5, so 0.5 times 1 minus 0.5, that equals 0.5 times 0.5, which equals 0.25. Right? So that's why that part just equals 0.25 then, and you're also going to round that up to the next integer. So remember, we talked about the idea of a ceiling, right? So a ceiling rounds up to the next integer. Right? And don't forget also that rounding up the ceiling, that's different than just rounding in general, right? So if you need to revisit that, please do, right? So that's what we get, right? And then so if the estimate of p hat is unavailable, right, then that equation would be n equals the ceiling of 0.25 times z alpha divided by 2 divided by e quantity squared, right? And remember, the ceiling means always round up. So if we have the ceiling of 1.2, that's just equal to 2, right? Remember, you always go up to the next integer, right? All right, so now we're ready for the last example, example 9. So this is an example just applying this. So what we're told, so a researcher wishes to estimate the proportion of households that have broadband internet access. What size sample should be obtained if she wishes the estimate to be within 0.03 with 99% confidence if blank, right? And then we have different conditions. So the E value is this 0.03, right? That's my margin of error. And so in part A, it says she uses a 2009 estimate of 0.635 obtained from the National Telecommunications and Information Administration, right? So in other words, what we have is a point estimate, which is p hat equals 0.635, right? And so another thing that's missing from the equation, we know E, we know p hat, we need to know what the critical value is, z divided by 2. So if you look at that table for 99%, that's equal to 2.575, right? So now that I know all those pieces, now I can figure out what n should be for A. So n is equal to the ceiling of p hat times 1 minus p hat times the critical value z of alpha divided by 2 divided by e quantity squared, right? So this is equal to, so plugging my values in, 0.635 times 1 minus 0.635 times 2.7, nope, it's 2.575 divided by 0.03 quantity squared, right? So if we simplify that, what we end up with is taking the ceiling of 1,707.57, which this equals, so we round up, so that would be 1,708, right, would be my n value that I need. Right, so then in part B, if we're not using any prior effort estimates, remember we're assuming that p hat equals 0.5. So that equation, right, is n equals the ceiling of 0.25 times the critical value, z of alpha divided by 2 divided by e, quantity squared. So this would be equal to the ceiling of 0.25 times 2.575 divided by 0.03, quantity squared. So this becomes the ceiling of 1,841.84, which equals then 1,842. Right? So we get both of those values. So we can actually find these two values using Statcrunch as well, so I can show you how to do that really quick. One thing to keep in mind though is doing it by hand versus technology. Remember that you might be a little off because of rounding error, right? So like the z alpha divided by 2, we're rounding those, for example, when we're doing it by hand, the critical values. So if I go to stat and then proportion stats, and then I want to go to one sample again, and then what I want to do is go to the width slash sample size. Right, so for part A, what we need to do is fill in the confidence level, which we wanted 0.99. And then we wanted the target proportion. Right, we plug in the target proportion of 0.635, right? In other words, that's where you put p hat, and then the width, that's going to be equal to 2 times your standard error, right? 2 times e, right? So in the width, you're going to plug in 2 times e, which would be 2 times 0.03, which is 0.06, right? So the width, 2 times e. Hit compute, and I get 1,709, right? So doing it by hand, I got 1,708, right? So we're a little off by doing it by hand, but we get a similar result, right? So then the one thing that changes to get part B is, since we're not assuming a population, a point estimate. Remember, we plug in 0.5 in that case, right? So for part B, we assume that p hat equals 0.5. So if I plug that in here, everything else would be the same, right? This would be 0.06 still. My confidence interval is still 99%. I hit compute, I get 1,844, right? Which again, I'm a little off from part B, but that's because of the rounding error for the critical value. So I get 1,842 doing it by hand, right? So that's how you do this using Statcrunch, right? All right, so that's all I have for this section. So let me know if you have questions. Thanks.